Hi there everyone, welcome back to the channel. I'm the GCSE science teacher. In today's video, we're going to be learning about electromagnetism and the motor effect, specifically focusing on Fleming's left-hand rule. If you do enjoy this video and you found it helpful, feel free to give it a thumbs up, share this with someone else to help them with their own revision. And so you don't miss out on any key revision for your GCSEs, please subscribe, join this amazing community, and thank you so much for all of your support. Let's get started. So first of all, we need to know about magnetic fields around a wire. Now, I did do a video recently on magnetism, and I highly recommend you go back and check that one out. If you've missed it, I'll link it for you. But you do need to know about this idea of a magnetic field around a wire, because when a current flows, it does create a magnetic field. And this kind of has like a circular field, unlike the one you see in a bar magnet, which has a slightly different shape. And what's really key to know about this is the strength of the magnetic field actually starts to increase when the distance from the wire decreases. So the closer you are to that wire, the stronger the force of the magnetic field. And also, if we increase the current in the wire as well, the magnetic field strength will also increase. Now, we can actually see this and see the shape of it if we were to use a compass, because remember, a compass will actually act as a bar magnet and will be attracted to that magnetic field and show the direction from north to south around that wire. We can also use the thumb screw method by using simply our right hand. So if we're to hold up our thumb like this, and we can see that our fingers curl around that wire, if we imagine we're holding a wire, our fingers will actually act as the magnetic field where our thumb is pointing in the direction of the current. Also, just be aware, in this topic, there's quite a few calculations and symbols and units. Remember, the symbol is the symbol for the word, whereas the unit is what it's measured in. So current, the symbol is I, whereas the unit for current is A, or amps. That's one of the key misconceptions here. So let's have a look at what happens if we get that linear piece of wire and we were to coil it up into what we call a solenoid. Now, with the solenoid, that coiled piece of wire, because it's coiled up, we can actually see the magnetic field lines actually change shape to resemble that of a bar magnet. Now, the reason for this is because the small magnetic fields are caused by the current in that wire, and they each add together to make a stronger overall magnetic field, which you see in this diagram. Now, we can strengthen that magnetic field simply by adding an iron core to make the solenoid an electromagnet, and this again will increase the magnetic field strength. So if you're a higher tier student or a triple scientist, you'll need to know about something called the motor effect. Now, the motor effect is the effect where a force is exerted on a wire when it is carrying a current in a magnetic field. Now, I'm going to give you a few different examples of this, because you do need to know about a calculation, and you also need to predict the direction of force as well. So let's go with the calculations first of all, with the force being equal to the magnetic flux density B times the current times the length. Now, magnetic flux density sounds quite complicated, but all it means is the strength of the magnetic field, and it's given the symbol B, but remember the units for that is Tesla T. It's the same with current, it's given the symbol I, but it's given the units A for amps. Length is L, the units is M. Often students get those mixed up, so just be very careful. Force is of course measured in newtons. So let's have a go at some examples then. We have 3 amps of current flowing in a wire that is 10 meters long. Calculate the force acting on the wire when the wire is placed in a 0.3 Tesla magnetic field at right angle. So let's have a look at how we calculate this. We have force is equal to BIL. So 0.3 times 3 times 10 gives you an answer of 9 newtons. Now, if you type it, you must write it. If you've been here for a while, you know this is what I always say when we do calculations in science. Don't forget, anything you type in your calculator, you must write it down as evidence. So here's an example for you to do. The answer will be in the description box, but feel free to comment in the comment section and let me know how you do. So 1.4 amps of current flows through a 5.6 meter wire. Calculate the force on the wire when the wire is placed in a 0.2 Tesla magnetic field at right angles. Let me know, don't forget your units, and good luck with that one. So the next thing you need to know is Fleming's left-hand rule, and you need to know that Fleming came up with this idea to help predict the direction that the force will exert on a wire which is traveling through a magnetic field. And you need to use your left hand. You need to make sure your thumb, your first finger, and your second finger are at right angles to each other. And the reason for that is because the force is greatest when the direction of current is at 90 degrees to the magnetic field. If it's parallel, there will be no motor effect, there will be no force exerted. So that's why we have to have it at 90 degrees. Now, you need to know what each of our digits represent. So our thumb will represent the movement or the force. The second digit, which is our first finger, will represent our field or our magnetic field from north to south. And our second finger, or our third digit, will represent the current from positive to negative. Now, this definitely gets easier with practice the more that you do this. So I really do recommend to practice, practice, practice. And I have some examples for you here, which you can try. So So if you have a look at this example, we have a horseshoe magnet. You can see north and south poles. You can also see a wire is traveling straight through the middle of it, and we can see the direction of current from positive to negative. Now, this is a similar diagram you'd see in the exam, which is why I've chosen this one. So what we need to do first of all is orientate our hand to make sure we know which direction everything is going in, because we're trying to predict the direction of force. So if we start off with the field, that's the one that I find is the easiest to navigate, and we can see the north and south is going in this direction. So if I point my finger out towards the south pole, which is towards the page or away from myself, so I would point this way first. Then I'd open up my thumb and my second finger, and I'll try and orientate the current next, because remember, the thumb is the movement, the direction of that force. So my current, my second finger, needs to go downwards, which is going straight through the wire, with keeping the first finger away from myself. Now you'll see my thumb is actually pointing in the right direction, which is why my answer, as you can see, is the right direction. But what happens if we flip the magnet? What happens to the direction of the force? Now, you're probably thinking it will turn to the left direction, which you're right. As you can see there, the answer is the left. But we want to prove this as well. So we'll do the same thing. We'll make sure we start off with the field, which is going now from this side. We're now going to turn this way. So it's pointing towards myself. I'm going to open my finger like this. So it's a bit of an awkward angle, but it is pointing towards myself. The current is going downwards. So we'll actually have it looking something like this. And you'll see my thumb is pointing out this way. So it's a bit of an awkward way of doing things. You do have to practice this, but just keep yourself practicing, and it does get easier. So yes, it is in the left direction. So let's have a go at if the current is in the reverse direction this time. So what we're going to do is we're going to put our first finger out from north to south and open up our thumb and second finger. We're then going to put our second finger upwards towards the sky, which is where the current is flowing from the bottom upwards. And as you can see, my thumb is pointing in this direction. So that's why the force is acting in the left direction. So again, it's all about practice. And I have another example for you guys to try yourself coming up now. So here is another example. We have the equipment set up here. Have a go at practicing this. I will leave the answer in the description box for you, but do write down in the comment section your answer. It's always good to hear from you guys. And that's it from me today. I've been the GCSE science teacher and you have been curious. If you did enjoy this video, please do like the video, share this with someone else, especially if you know of anyone who may be in your class or maybe a relative or a friend who is definitely doing their GCSEs or taking an exam that would really benefit from learning more science. It's always good to help people out, so feel free to do that. And of course, if you'd like to subscribe to join this wonderful community, please do click subscribe now. Join us. Thank you so much for your time and your support. I do appreciate it. In the meantime, have a fantastic day and I will catch you in the next one. Take care.